Fred's chore this weekend is to water the lawn, but it is taking forever. He's having to walk all over the lawn to get the water there. He needs to come up with a way to do this faster because he wants to go hang out with his friends. How can Fred water the lawn faster? To answer this question, we're going to talk about hydrodynamics. Up until now, we've talked about hydrostatics. That is, when a fluid or water is not moving, it's static. Now we're going to talk about hydrodynamics. Again, we have fluid or water, but now it is dynamic, meaning it is changing. Hydrodynamics is when fluids are in motion. To study hydrodynamics, we have to set up some conditions. First, our fluids must be non-viscous. That means they have no internal friction. Next, the fluid must be incompressible, or its density must be constant. Finally, the motion of the fluid must be steady and non-turbulent. Let's consider a fluid flowing through a tube that starts wider and gets smaller. We're going to consider a volume that's the same. So volume 1 here and volume 2 here, we're going to say are equivalent. This one is thinner, but it has a larger area. And volume 1 is equal to area 1 times delta x1. The volume 2, which is this volume here, is equal to area 2 times delta x2. We'll define them from the beginning as being equal volume. Now, since there's a fluid flowing through it, we're also going to have a velocity for each. The velocity at this point is called v1, and the velocity in this fluid we'll call v2. Now, if you recall, velocity is equal to change in x over time. Delta v1 equals a1 delta x1. Delta v2 equals a2 delta x2. Now we're going to replace this with the velocities by rearranging this to say velocity times time equals delta x. Now we're going to consider this over the same time to see what those velocities are. So we will be able to cancel out these two times. And this leads us to the continuity equation. The continuity equation tells us that at any 2 points, the area of the tube times the velocity at that point is equal to the area at any other point times the velocity at that second point. So the continuity equation says the volume of fluid entering one end in a certain time interval equals the volume leaving at another point in the same interval. This makes sense because our fluid can't be compressed. And again, we write the continuity equation as A1, that's the area at point 1, times velocity 1 equals A2 times velocity 2. The result is that if the area is larger, you will have a slower velocity. So at any point where there's a large area of a tube, your velocity will be less. Any point with a small area, you will have a faster velocity. There's one more term that we use when we talk about fluid flow, and that is volume flow rate. The volume flow rate stays constant throughout the tube, and the volume flow rate is just how much volume passes per unit time. You can also write it as VA, and that is always going to be a constant. So how does this help us with Fred? Well, if we can use the equation, if we reduce the area that his water is flowing through in the hose, we can increase the velocity with which it's traveling. Because if I have a smaller area, I'm going to have a larger velocity to keep this as a constant. When we put a pointed nozzle on the hose, the result is that the water will flow faster, and he won't have to walk all the way to the other side of the lawn to water it. Now note, he will still have the same volume coming out of the hose per unit time, so the flow rate didn't change, just the velocity coming out.